Alright, so here's another trinomial factorization problem, which is perhaps a little more complicated than others, because here you have a leading coefficient that's not equal to 1. In this case, it turns out being a 7. So the factors that go into making this 7 from the product of the first terms in the binomial breakdown you're going to get from this do play a role, not only in getting this 7, but in also constructing the coefficient of the x in the middle, this 19. Now, just like with trinomial factorizations with leading coefficients 1, you got a couple of ways that you can go about this. And I'll demonstrate them both, and then you can pick and choose which one you like best and use it at will. They're going to turn out to be equivalent. But I suppose one way to do this is just to kind of try to observe the result away. You've got a trinomial here, so that trinomial has been generated by the product of a couple of binomials, so you just sort of look things over and play with things until you find a combination of coefficients that fits. And especially with practice, you can get really good at this and sometimes finish these kinds of things off really quickly. So if you look at this, for example, here, you got an x squared as part of this 7x squared at the beginning. So when you think about our integer-based factoring techniques, the only way you're going to get x squared really is by having at least a factor of x in each of the first positions of both of the binomials, because when you multiply this out by FOIL, x times x gets you an x squared. So in this case, since the leading coefficient is not 1, that's not quite enough. There has to be some kind of pair of factors that you multiply out to get 7, and in a sense we're lucky here with that 7, because 7's prime, the only factors of 7 are 1 in itself. So we could make this 7x, have this be an understood 1x here, and bingo bango, there we are. That first product, 7x times x, gets you 7x squared. Now, the minus 6 at the end now, well, that has to be the product that results from multiplying out the last entries in each of the two binomials. And you got a little more variation here with this 6, because there are more factors than just 6 and 1 that'll multiply to 6. I guess you've also got 2 and 3. But the thing is, you have to be careful, because this is a minus 6, so one of those factors is going to be positive and one of them is going to be negative. And then you have to pick factors of 6 that interact with the factors of 7 that you've already got from factoring down the 7x squared at the beginning, so that when you do the outer and inner products of the FOIL, you end up getting a combination of 19x in the middle. Now, again, depending on how much comfort you have with this could be laborious and drawn out, or it could be really quick. I guess I tend to think first of two combinations of 2 and 3 multiplying to 6. And when I think about it here, I want a 19x, a plus 19x in the middle. So let's see, I could get, say, a 21x by having a plus 3 in this binomial, finishing that one off. And then in the first binomial, I could have a minus 2. So you can see minus 2 times 3 is minus 6, so we're definitely getting that last product to work out there. But I've also chosen carefully enough so that if we actually multiply it out, the outer and inner products here, you can see the outer product is 7x times 3, that's a 21x. The inner product is minus 2 times x, that's a minus 2x. And 21x and minus 2x combine to that plus 19x in the middle. So there's a perfectly good way of getting this result. I mean, again, depending on your level of comfort and how much practice you've had kind of observing things and trying different combinations of different factors until you get some arrangement that gives you that x in the middle, this could go quickly, it could take a lot of time. Just because it can potentially take a lot of time, there is an alternate approach to this based on grouping. So let's take a look at a grouping-based approach on this. Just trying to turn this 3-term polynomial into a 4-term polynomial. So let me bring down the original 7x squared and the minus 6 that we started out with. Now, if the leading coefficient were 1, again, we just focus on the factors of the minus 6. But here, again, the leading coefficient isn't 1, it's 7. So the factors of this 7 interact with the factors of this minus 6 to get us that 19x in the middle, and we already witnessed that here when we actually went through the outer and inner product multiplication. So because you want to bring both the minus 6 and the 7 together in this process of dealing with the coefficient of the x in the middle, what you do with this grouping-based approach is you start out and you literally multiply those leading and constant coefficients together. So if you did that here, if you took 7 times minus 6, you can see that they multiply out to minus 42. Now that product right here contains all the information tied up in it about basically all factors of 7 and all factors of minus 6. So basically you can run at this with a grouping approach now by asking yourself, okay, this minus 42 has all set factors of 7 and all factors of minus 6 potentially wrapped up in it. What factors then of that combined multiplied out minus 42 would combine to the coefficient in the middle here, this 19? So when you look at this minus 42, again, here's where a little more playing around is probably required, but it's a little more focused. You're just looking for factors of just this minus 42 that would combine to 19x to the 19 in the middle. Well, when you think of those factors, it might take a little bit, but factors that do that, it turns out, are 21 plus 21 and a minus 2. You can see 21 times minus 2 would give you minus 42 as a product, but you can see that 21 and minus 2, when you combine them, give you exactly this plus 19x that you're worried about in the middle. So this observation, multiplying the leading by the constant coefficient and then finding factors of that product that combine to the middle x term coefficient, give you a grouping-based way of taking this 19x in this case and breaking it down into the two parts generated by the outer and inner products from the FOIL of the factored form. So let me go in there and just replace this 19x that we started out with this decomposed form of plus 21x minus 2x. So there's a breakdown that should give us a reasonable result here. So now we've taken this trinomial setup and we've created, by kind of decomposing the outer and inner products into their component parts, a 4-term polynomial setup that should yield to grouping. So when we've grouped things up, here's the first little group. Looking at it on its own, you can get a 7x out of both of the terms there. That leaves behind an x plus 3. And then when you look at the second little group here, you can take out a leading negative and a 2, and that leaves behind that exact same leftover x plus 3. So there's again the indication that the grouping's been successful. You've got exactly the same leftover trinomial piece here. So you factor it out as common. There's the x plus 3 coming out. That leaves behind a 7x minus a 2. And you can see now, yeah, the order of this factorization, the way we did it with grouping here, ended up being the opposite order of this. But when you think of multiplication in the real number system, order doesn't matter. 2 times 7 is the same as 7 times 2. So just as with numbers, so with polynomials, 7x minus 2 times x plus 3 is the same as x plus 3 times 7x minus 2. Now, just as a final note here, there's nothing that said I had to put in 21x minus 2x in the middle here in exactly that order. I could have done the opposite order and gotten just as good a final result. So if I ran that here, if I had started out with my 7x squared at the front, my minus 6 at the end, and when I noted that my factors of minus 42 that combined to 19 were 21 and minus 2, if I put them in the opposite order, put in minus 2x plus 21x, that's still going to give me a good grouping. So when I would group things up, my first terms versus my last terms here, and perform little greatest common factorizations on each group, I'd be able to get an x out of the first little group. That would leave behind a 7x minus 2. I could get then a 3 out of the second little group. That would leave behind that same 7x minus 2. And you can see now, this time the 7x minus 2 is the common leftover binomial factor. So to finish off the grouping, you'd take it out first, and then just write out the leftovers from each term. That would be an x from the first little term and then a 3 from the second one. So there's the kind of opposite order look to what we had before. So how you decompose that middle term in your trinomial with this grouping approach doesn't really matter. Once you've picked out the factors of the constant coefficient that combine to the middle coefficient, you can see you can put them in either way. You're going to get exactly the same factorization because, well, order of multiplication doesn't matter. Whether you factor out that x plus 3 or that 7x minus 2 first, you're getting the same result either way. So there are a couple overall ways of running this. Again, if you're good at observing combinations of factors that combine to what you need, do it. It's perfectly good. It's perfectly valid. You get exactly the proper and correct answer. But if you're having some trouble finding some combination of workable factors to combine to your x coefficient in the middle, then you might want to consider this grouping approach. Take the product of the leading times the constant coefficient, find factors of that product that combine to the coefficient of the x in the middle, use those to decompose that x term in the middle in either order, and then factor by grouping, and you'll get a result that's just as valid, just as accurate, and exactly the same as the one that you'd get by observing things directly.